This is hybrid functional maps for Crease-Aware non-isometric shape matching. We aim to obtain correspondence between two input triangle mesh shapes that allows non-isometric deformations in general. One of the very popular and well-studied family of solutions are based on functional maps. The very essence of functional map method is the transitioning from spatial to spectral, namely a spectral decomposition into a set of scalar basis functions on the shape, associating each vertex point with additional values as their new spectral embedding. This effectively transitions every point from spatial into high-dimensional spectral space. Here we can see slices of its projections in a 3D space. The benefit is that two shapes can now be aligned with a linear transformation, a k-by-k functional map, and correspondence can then be obtained by a nearest neighbor search in the aligned spectral space. Existing functional map methods use eigenfunctions of the Laplace-Beltrami operator as basis functions. This is also an extremely well-studied tool. One of its definitions, which will be useful for us, is given as the Hessian of the Dirichlet energy defined over all possible scalar surface functions. In other words, it's a measurement of the smoothness of a function on the shape. As a result, its first few eigenfunctions are associated with the smoothest surface functions, aka lowest Dirichlet energies. The first three, for example, assign the smoothest possible function values along three different principal directions. Thus, the embedding abstractly resembles the shape smoothly and on a global scale. Smoothness serves as its power, but at the same time also its weakness. It struggles at supporting detailed structures. To see that, we can visualize a correspondence by transferring quantities from source to target that may be colors, normals, or can be vertex positions. For a correspondence that is encoded by a Laplace-Beltrami functional map, it struggles with delicate details like limbs and tails. This may not be obvious from color maps, but they're well captured by normal maps or vertex maps. To counteract this, we consider an elastic basis function introduced recently by Hadovich et al. They come from eigenfunctions of the Hessian of the elastic energy defined over all possible surface deformations. In other words, it's a measurement of the amount of stretching and bending of a shape deformation. As a result, its first few eigenfunctions are associated with deformations that are the easiest bended or stretched, aka with the lowest elastic energies. Since the deformation is given by vertex displacements instead of scalars, they are projected onto the normals, resulting in scalar-valued basis functions, like before, but which are no longer orthogonal. This has three most prominent differences over the Laplace-Beltrami basis. It first supports high curvature regions, for example, on thin structures like limbs and tails. It is Crease-Aware due to the curvature sensitivity. Lastly, it is extrinsic instead of intrinsic. These strengths makes it well-suited to match details from thin structures and curvature features, and results in very pleasing normal transfers. However, at the same time, the elastic basis is also more prone to confusions from local similarities, resulting in relatively inconsistent matches across larger regions. To remedy the deficiencies for both bases, we propose the hybrid approach. This motivation is natural as their strengths and weakness complement each other, and thanks to the linearity of the function map framework, the formulation is straightforward. We pick the first few eigenfunctions from both operators and use them as hybrid basis embeddings. Notice how the elastic embedding, which is more local, naturally extends to the global ones. This can now easily encode a reasonable correspondence in our previous example with as little as 60 bases, whereas the other two still struggle with more than 200. To show you one more example in practice, these are the results from a state-of-the-art function map shape matching pipeline. Notice how the hand and fingers are most properly mapped with a hybrid adaptation. Recall that the elastic basis becomes non-orthogonal after vector to scalar projection. In order to make this happen, we need to accommodate function map with a non-orthogonal basis in a deep learning framework. Advocated by Hadovich et al., a proper tool to handle this is the Hilbert-Schmidt norm. Specifically, we extend the adaptation from axiomatic formulations to deep function map solvers, allowing general usage in most existing function map methods. With a sprinkle of linear algebra, we arrive at a closed-form differentiable solver as a direct plug-and-play to the classical ones, with one downside. The Kronecker product expansion results in a single k-square by k-square linear system, as opposed to k-independent k-by-k linear system from before. In practice, this means that the memory and runtime cost goes off the chart as the spectral resolution approaches above 100. This is where our hybrid approach comes to the rescue again. Notice the two block structure presented in a hybrid function map, as the two energies are expected to match with each other. With some mild assumptions, we can effectively solve them separately and drastically cut down the cost. Equipped with this, we're now able to adapt hybrid function maps to most existing pipelines at an optimal basis ratio with little computational overhead, even for large deep function map systems, at a relatively low effort, and finally, in most cases, we should expect overall performance improvements. We've picked 3 representative methods from axiomatic, supervised, and unsupervised learning methods, evaluated them across near isometric, non-isometric, and topologically noisy settings, and we're able to observe overall performance improvements, especially in challenging cases up to 15 to 45% better mean geodesic errors. We've provided our code at the link here. This includes everything you need to reproduce our results and for your own easy adaptations. Thank you very much.